Hi, and welcome to this 9th video in this acid and alkali series. And in this one, we're going to look at what is potentially one of the most complicated calculations in this module, which is that of calculating the pH of a buffer solution and then subsequently calculating the pH after we have manipulated the buffer equilibrium by adding either a small amount of acid or base to that solution. So what we'll do in the first instance is we will create an acidic buffer using ethanoic acid, as we have looked at before, and this will create an equilibrium between the parent ethanoic acid and the corresponding salt base part of that equilibrium, and that will be in conjunction with its hydrogen ions, giving rise to its pH. And what we will do is we will say that the ethanoic acid is a 0.1 molar solution, and to that solution, in order to create a buffer, we will add, this time we'll directly add a 0.05 molar solution of the corresponding salt. We'll add that as, say, a sodium ethanoate salt or something like that. In the previous videos, what we had done was reacted that with sodium hydroxide to directly create the salt part of the equilibrium. But if we already have a stock solution of the ethanoate salt, as I say, such as a sodium ethanoate salt, we can add that directly to the ethanoic acid and set up the buffer in a direct manner that way. And what we'll do is we'll say, for argument's sake, we will use 1 litre of that solution, and we'll say the temperature is 298 Kelvin. Now, for this, obviously, we're going to need the pKa as well of the ethanoic acid, and we know that this is 4.76. We can get that from literature values. And so what we're going to need to do is calculate the initial pH of this buffer. And so we know by now that the initial pH is equal to minus log base 10 of the H plus ion concentration in that solution. And what we have to do is use the equilibrium constant for this equilibrium and say that if Ka is equal to H plus, which is the term we are going to want to calculate, multiplied by the ethanoate salt concentration, which we know what that is, and divide that by the parent acid concentration, meaning that if we were to rearrange this equation, we would be able to generate H plus. We've done this before, and we would know that that is equal to Ka multiplied by the acid. Now I'm going to call the acid HA at this point and call the salt A minus, just to make these equations a little bit more simple and a little bit more generic, which means that if we were to numerically calculate this, remember, going from pKa to Ka means that we have to use 10 to the minus power, so that's going to be 10 to the minus 4.6. That will generate our Ka directly, and we know that Ha was the parent acid, which was the 0.1 molar solution, and we know that the salt component was 0.05. That will allow us to calculate the H plus ion concentration, and that will come out when you plug the numbers into your calculator, will give you a concentration of 3.48 by 10 to the minus 5, which, when we then calculate the subsequent pH, will give us a pH of 4.46 to 2 decimal places. Now, that is the initial concentration of the buffer. Now, if we were to potentially manipulate this by, in step 2, so call that step 1, in step 2, what we're going to do is add 0.005 moles of sodium hydroxide. So we're going to add a base to this buffer solution. Okay, And what we'll do is we'll add the 0.005 moles as a solid so that we then don't have to change the volume. You can do this by adding a solution, but this will do the same calculation, but it will change the resultant volume. So you have to be careful of that in calculations. And if you'd like me to do some of those, just let me know in the comments part of these videos. But for now, we'll just add a direct solid and show you how to manipulate this calculation. And so if we were to add the base, we would have a hydroxide ion. That is going to react with the parent acid, the HA concentration. So again, we'll keep the HA, meaning the ethanoic acid. And that's going to react to create more of the salt, the ethanoate, plus some water. So it's going to give us salt plus water. Now, if we know that we've said we're going to add 0.005 moles of the hydroxide, and we know that initially, if we had a litre, then we know we have 0.100 moles of the HA, and likewise, we know we have 0.05 moles of the A minus. The water we don't need to worry about because that's not involved in the Ka calculation. And so, if the hydroxide is going to react with the HA concentration, this value is going to go down by the corresponding amount of moles. So that's going to go down by 0.005, leaving us with 0.095 moles of HA, and subsequently 0.095 moles per litre, because we know the volume is, as we said up here, the volume is 1 litre. And so, likewise, the 0.05 as a product of this reaction is going to increase by a small amount of moles as well, giving rise to 0.055 moles here. And subsequently, because we're in 1 litre, it's going to be moles per litre there. So we now have the number of moles and subsequently concentration of HA and also A minus after the subsequent addition of a small amount. Remember, buffers are only able to compromise pH on small amounts of addition of acid or alkali, not a huge amount. But on the addition of this small amount of moles, we have these new concentrations, moles and subsequently concentrations of the HA and A minus concentrations, which means that we can then simply recalculate this aspect of the calculation again, leading us to a H plus, and we just simply do the calculation again, but this time with the new numbers. We know that again, Ka is 10 to the minus 4.76, so I'm using this equation here, this Ka times HA divided by A minus part. So we've got 10 to the minus 4.76 multiplied by the new HA concentration, which is 0.095, divided by the new A minus concentration, which is 0.055. You churn those numbers and you get a concentration of 3.00 times 10 to the minus 5, which when you plug that into the pH log base 10 equation, gives you a pH for the buffer after reaction of 4.52. This is giving you a change of 0.06 pH units. Remember, a question sometimes may finish off by saying what is the change, and so subsequently you'd have to do some sort of pH subtraction to work out what the difference in your initial pH and your final pH would be. So the final pH would be at 4.52. The initial pH we calculated was at 4.46. And so that very nicely demonstrates how stable a pH of a buffer can be within that buffer region of a titration curve. And for comparison values, if we had added this 0.005 moles of sodium hydroxide to a solution of water, that would have actually given a pH of 12.7. So that would have been quite a substantial change of pH. This pH change is only a change of 0.06. So if you wanted to have a look at that calculation, as I say, 0.005 moles into 1 litre of water at pH 7 should give you a pH of 12.7 after you've manipulated Kw. You can try that one on your own, but as I say, for buffers, this will give you a change of 0.06. So thank you very much. As I say, this is arguably the most complicated pH calculation we can get to. It can be changed by adding volumes of sodium hydroxide, and so sometimes you may have to recalculate these concentrations down here. So these values here may change slightly because we were not using volumes of 1 litre, so that could be potential trip hazards within a question, so be careful where the volumes are 1 litre or change if we've added solutions. So just be aware of those in calculations, but as I said earlier, if you want me to look at a few of those examples, let me know and I can work through some of those examples for you. But as I said, thank you very much and good luck with these, and I will see you in the next one.